Okay, so let's look at this problem. So I want to determine the internal shear force and bending moment at point C. So just to kind of help you visualize that, let's draw a big line there at C and say, this is where I'm going to cut it. And do I want to look at the left side or the right side?
No.
Mr. Randolph says left. Anybody else like left? This is not a political statement, so you can say left and not feel be ridiculed. Or right. I don't see any advantage to either side. The loading on both sides is the same. The number of reactions are the same. So, you guys like left? We'll go left. So if we go left, we're going to need to know the reactions at A. So I'm going to use my drawing as my free body diagram. So I'll come over here and say I have a reaction AY and a reaction AX.
Mm-hmm. But I thought it would have less reactions than B. It's on a roll down.
No, AX is probably going to be 0, so it doesn't really. It's not going to be that much extra work. Okay, now I'm going to come back, and for my ease of finding the reactions, I'm going to take the distributed load and find a concentrated equivalent. So the concentrated equivalent force is the area under the curve, the loading curve. The loading curve is a rectangle, so it's just base times height. The base is 18 times the height of 3, what is that, 54? So that's 54 kips. And it would be right in the middle, and the centroid of a rectangle is right in the middle, so that would be 9 feet.
How did you get 50?
You can do this.
3 times 18?
3 times 18, okay.
3 kips per foot times 18 feet.
Okay.
So I'm going to come over here now, and I'm going to sum moments about B to find my reactions at A. So about point B, using right-hand rule, my concentrated equivalent force of 54 creates what kind of moment? Positive. So I have 54 kips times 9 feet. And then I have my AY reaction creating negative moment times 18 feet. It looks like AY is half the total load, or what, 27? That makes sense? Is that right? Anybody out there? I see a lot of faces. Does that equation give me 27? Let's hope so. So now I'm going to sum forces in the x direction, which is a little more work, but it's a pretty easy equation to solve. All I have is AX, so AX is 0. So I have my reactions. So now I'm going to draw a free body diagram of this left-hand side. I'll draw it slightly larger, so give me a little more room. So there's the 6 feet, and then on top of that I have my distributed loading, which is 3 kips per foot. On the left-hand side, I have my AY reaction, which is 27 kips. And then I'm going to look at this face and assume positive shear force, which is down. So this would be the shear at C. Positive axial force and positive bending moment. Everybody see that? So there's my free body diagram. So if I gave you a problem like this on the exam, if you got to this point right here, you're more than half solved as far as I'm concerned. This is if there is a skill or a thought process, this is it. Drawing the free body diagram, identifying all the components and the internal forces that act on it. At this point, it should be a fairly simple application of our 3 equations of equilibrium. So I'll begin with summing moments at the cut. And I'll assume right-hand rule is my sign convention. So there's a lot of information being conveyed here. I'm summing moments about the cut, yeah. I'm using right-hand rule, and I'm in equilibrium. So with that as right-hand rule as my guide, this moment is positive or negative? Positive. I think you can see I need to go ahead and take my distributed force and for convenience make a concentrated equivalent. So what would that value be?
18.
Yeah, it's a rectangle, so the area of the curve is base 6 times height 3. So that's 18 kips. And its moment arm from the cut is half the distance, so that should be 3 feet. And that force creates positive or negative moment about the cut. Positive. So there's my 18 kip force times 3 feet. And then I have the reaction, 27, that creates positive or negative? Negative. So I have 27 kips times 6 feet. So from that, I should be able to solve the moment. It looks like it's going to be positive. I don't know what that is off the top of my head. Somebody calculate that real quick.
108.
108? Anybody else get 108? Yep. And that will be kip feet. So it says I have a positive bending moment. Now going back and looking at our problem, does a positive bending moment make sense? How do you think that beam is going to bend? Is it going to bend up or down?
Down.
It's going to bend down. In fact, it's going to look something like that, which looks like a big smiley face, right? Positive. So you should expect positive moment pretty much the entire beam. So that matches that insight. Now I'll come back and sum forces in the y direction. I'm assuming up is positive, so what kind of force is this? It's acting down, so that's minus. My concentrated equivalent force is down, that's also minus. My reaction is up, that's positive. So it looks like the shear at C is equal to 9. That makes sense? So this tells me I have positive bending moment at C, positive shear force at C, and this last equation is pretty straightforward. If I sum forces in the x direction, all I have is the axial force, and it looks like for these loads it's 0. And that's it. Any questions about that one?
So why don't we have to solve the other side now?
Well, you'd get the same result.
Why don't we have to solve it first one, then we got to do it?
Because we passed under a point load.
Oh, okay.
So here we have a continuous load, right? So I can cut a continuous load and not have to worry about, do I have to be to the left or right of it? Mr. Hudson.
So
sorry.
if C happened to fall under where the point load and the distributed load occur, would you have to do both sides?
That won't happen.
It won't happen.
Because what you're suggesting is if I cut the beam in the middle, right?
Yeah.
When I cut the beam in the middle, my equivalent load will still be over here on the left.
Okay.
So I'm glad you brought that up, because that's kind of a common error. Is what students will do is they'll replace the distributed load with this 54 and then think it's an applied concentrated force from that point on. So they will try to come in here and say, oh, that 54 at 9 feet, that's off the body. It's over here, and they'll have no load applied to this segment. Can't do that. That's a different problem. So remember, when you cut the structure, I'll cover it up. You have to work with everything you see on the left-hand side.
If we were to cut it to the right, make sure we just found 154 point.
You would have to deal with everything you see on this side. You'd have to find the reaction at B. You'd have a much larger. You would get exactly the same values. You would still get that moment, and you would still get that shear, and you still get that axial force. You get exactly the same values with exactly the same signs. Because remember, this is a positive bending moment. Right? And you can see that no matter where I cut this structure, what's the bending moment going to be? It's got to be positive. So, positive everywhere. I'm sorry, what's your question?
So, because it's continuous, because it's equal it has equal weight, like on the whole table, it does, like, we can cut it and it'll be fine.
It doesn't matter that it's equal weight.
But because, like, this, like, one load, I can't cut it here.
Point loads give us an issue with summing forces.
Okay.
If I have an applied couple, we'll have the same kind of issue when we sum moments. Do we include the couple or do we not? Are we cutting it just to the left of the couple or just to the right of the couple? Applied couples and structures are really less common than applied forces.
Okay.
All right, so we'll stop this here.